Okay, so we're going to take a look at this particular graph, which is kind of a nasty little function, which is the purpose. We don't necessarily want to work with that particular function. It's icky. It's got e to the x. It's got sine of 2x. We've got a lot of irrational behavior. It's just not what we want to do. So let's just say, for the sake of argument, that our model, we're only particularly interested where a is equal to 0. We're not interested in the whole graph, but we're really particularly concerned with what's happening around a to the 0. So in particular, we're curious about the behavior of the graph right there, which if we zoomed way in, looks like it might have some linearity there. That function looks less curvy than maybe other parts of the graph. Now, I want to point out that the part on the right, if I kind of divide this into two parts, the part on the right there, that looks pretty linear. In fact, that part in the blue looks highly linear. But once we move over to the left side, that part looks a little bit less linear. It has a little bit more curve to it. So we have a difference in the behavior. But in particular, we're focused on the pink and that blue area, the space around a equals 0, or where the x values is 0. So go ahead at this point and use that function to find an L of x where a equals 0. And I'm going to pause and let you think about that. Okay, so the first trick is realizing that this is not quite as simple as a derivative. Y prime is going to be equal to e to the x sine of 2x plus e to the x cosine of 2x chain rule times 2. So I did some simplification. It's e to the x sine of 2x, 2 cosine of 2x. And so my y prime at 0 looks to be 2, because when I plug in 0 right here, oh, wrong one. When I plug in 0 right there, I get 2, because cosine of 0 is 1 times 2 is 2. That's going to be 0, and that's going to be 1. So 1 times 2 is 2. And then y at 0 is actually equal to 0 as well. We can see that on the graph. So my linearization is actually 2x. So that is a linear function that represents our curve at 0. That's the tangent line at 0. So now we're going to use that to find values close to 0. So flip to the next slide and call it L of x equals 2x. I would like you to find L of 1/2. And what this represents is the function in its linear model form at 1/2. And that's pretty easy. That's just 1. So this means f at 1/2 should be approximately 1. So now go ahead and find f of 1/2 in your calculators and see what you get. I'm going to pause. And that's the value I get via a calculator, and that was what was in my notes. So now we'd like to see what the percent error is. And the error can be represented as actual minus estimate, absolute value. That way it doesn't matter if you flip the estimate or the actual, over actual. And if you put this in, if you put the actual is 1.385, so I will highlight to color code. This is the actual. The estimate is 1. Okay. And if you plug this into a calculator, I get approximately 28.28 or 28% error. So that's a fair amount of error, but if you think about it, 1/2 is pretty far away from 1. The behavior was still linear, but it's starting to curve upwards. It's not a perfect line. So that means that there's some linear behavior there. It has a fair amount of error, but depending on your tolerance for your needs, it might be different, or it might be appropriate. It might be a reasonable amount of error. It just depends on your needs. So the next thing I would like to do is use your L of x to find L at -1/2. So this is on the left-hand side of 0, -1. So that means f at -1/2 is approximately -1. So you can imagine what I'd like you to do next. Let's go ahead and find f at -1/2, and then I'd like you to find the error %. So I'm going to pause and write those in and let you solve for them on your own. So this is the value I get. F at -1/2 is -0.5103779.515, and the error is a whopping 96%. That's a huge error, but it makes sense. 0.51 is approximately half, 1 is double that, so it's almost 100% of the actual values difference between the two. So it's a huge margin of error there, much bigger than the previous one. So let's examine why. So I graphed the linearization of this function at x equals 0, and what I found was that you can see the error. This is 1/2. So from there, let's see if I can be right there to right there, that's the error between the two, right in there. The difference between the error and those two and the error here is massive. Okay, so that is why there's a pretty big problem. It's a whole unit here, whereas it's a little bit less here. So you can see that the distance between the two curves. And it's because on this left-hand side, as we indicated prior, right here, it's curving away from the line more rapidly than on the right-hand side. It's curving away from the line less rapidly. So that's why the error, that's why the linearity works really well on this side, but it doesn't work so well on this side. So there's a couple things that you can take away from this second video. The first thing is that we can use linear approximations to come up with the function value when we don't want to work with the function at hand. If the function is nasty, when we can tolerate some error, those are appropriate times to use a linearization. Or when maybe we can't tolerate error and we need to come up with a really, really good linear approximation, that's fine too, but we need to be very conscious, and this is the second part, of how the graph is behaving and how far out we go from our a value. Yes, we can use linearization to approximate a graph. That's great. But we have to be really careful about where we choose our a value and making sure that that linear approximation actually works for the purpose that we're using it for, and we're not inflicting too much error here.